We have a school class. We have ABB gymnasiet from Västerås in Sweden. You have been kind of marinated this morning with the history of Alfred Nobel and his will and the Nobel Prizes, focusing on physics, of course. You are our VIP guests this morning. And we also have another VIP, which is Anders Karlhed from Stockholm University, also a member of the Kungliga Vetenskapsakademin, KVA, the Royal Swedish Academy. Welcome.
Sciences, thank you.
And also welcome all of you watching us on YouTube. And all of you in this room will be able to ask questions to us, to Anders, our specialist, via Mentimeter. You will get the code later on. You can ask questions in Swedish, of course, and also in English. But this morning, Anders, you are a part of the physics class at the Royal Swedish Academy.
Yes.
And this morning, the big decision was taken, or was it taken earlier on this year, or how does it work?
Well, the final decision was taken this morning, but it has been a long process ahead of that, and it's handled. The work is done by the physics class, but in particular of a small group, which is nominated within the physics class, which is the Nobel committee that does the work and prepares it. And then it's discussed at various stages in the whole physics class. And then finally there is a decision by the whole allmänna sammankomsten in the Royal Academy of Sciences.
Mm. So how many people is it in the physics class that take part of making the decision?
I don't know exactly. Well, maybe 20, 30 persons present, maybe a bit more actually.
Yes. But it's not only you, it's a lot of other people who can, professors?
It's professors from, it's constructed so that there's a number of positions for professors at Swedish universities, and then when you reach the age of 65, you're sort of outside of that, so then you are still a member, but then new members can be elected to the physics class.
Mm. I see. When you make the decision in the class, is it difficult to agree, or?
Well, that varies a lot. Often it's not, but there are certainly cases where it has been very difficult and very different opinions on what the outcome and what the prize should be awarded for.
All right.
But and if you want, you can go back and look what the discussions were 50 years ago. It's a 50-year secrecy on this material. Mm. But old prizes one can study.
Okay. And you're actually the only one in this room who knows who receives the physics prize?
I hope so. It's supposed to be like that.
Supposed to be. Can you just give us a hint?
No.
Just a small hint?
No. I don't want to destroy First, I'm not supposed to do that, and I don't want to destroy that for my dear colleague who will present the prize soon.
Is it difficult to keep quiet in front of families and friends, and are people trying to?
I don't.
Ask questions.
I think not really.
You are very well respected in your position.
I don't know. It's. I know that for the prize in literature, there have been lots of speculations and rumors, and also leaks. There were lots of scandals there. I haven't really encountered that. There isn't the same general interest, of course, in the science prizes, so it hasn't been an issue, as far as I know, and I have not encountered any questions.
I see.
At least not any serious ones that I have had any difficulty of ignoring.
Right. Yes. So you cannot say this year was more difficult than others?
I know I can comment afterwards, but we'll save that for later.
Well, the only thing that you have to, I want to walk backwards in time a little bit, back to 1895. In 1895, Alfred Nobel wrote his will, and this is his will. He has a very beautiful handwriting, and he writes that when he has passed away, there should be a prize, and someone who has come up with something or made something that is to the greatest benefit to humankind should be rewarded. And the areas he also wrote in his will were 5 areas. It was medicine or physiology, as we heard about yesterday. It was physics, as we will hear about today. And then chemistry, literature, and peace. And, well, to the greatest benefit to humankind, that's the only thing you have to, that's the only ground that you have to make the decision. It's very precise, at the same time it's very, very big.
Yes.
The greatest benefit to humankind, for me it sounds really difficult.
Maybe so difficult so you can't really fulfill that, but you have to do your best and choose really something that is important or has the potential to become important, because it's of course also the case that for many scientific discoveries it takes a very long or even very long time for them to be of any practical use. So that so basic research, curiosity-driven, is extremely important also for future applications. For example, the modern vaccines that was so impressive for the COVID, the mRNA vaccines were based on basic research done long ago. So this makes it really, really hard. So.
Yeah.
And it's not always that the prize has any direct practical application, but it's very seldom you can say that it can never have that.
Yeah, I see. What do you think about last year's prize in physics? The climate modeling.
Oh, I think that was an excellent prize, and that's certainly something that is very timely and where research has been very important. So that's something that connects very much to one of our existential problems and questions.
Yeah.
I think that was a great prize.
Soon we will look at the live streaming from the Royal Swedish Academy. I think it starts.
And it was easy to agree on that one, I should say.
It was easy to agree. Thank you, Anders. Yes, I think we will hand over to look at the live streaming from the KVA, Royal Swedish Academy, Kungliga Vetenskapsakademin. Or we don't know. There are a lot of people in this room who are looking at this, our live stream from the museum you cannot see, but I think it's more people in this room than it is at KVA right now. So there are a lot of people who are interested, teenagers, grown-ups, and all the others. So, Anders, you know all of these people who we will see right now?
Not all, I know some of them.
Tell us about the prize.
But maybe more interesting, I could say something about the procedure.
Yes.
I mean, the Academy gets lots of nominations from professors all over the world, from Swedish professors, but many international who are experts in various fields. And then the committee within the physics class decides on various topics and follows various fields, what's happening, where is it possible to have the same thing will happen, and then a fairly large number of scientific evaluations of fields are issued by by the physics class. So one gets these evaluations from international experts, and these are generally very well written, and they play a very important role. Now it's
årets Nobelpris i fysik. Welcome to the Royal Swedish Academy of Sciences and this press conference when we will announce this year's Nobel Prize in Physics. We will keep to our tradition and begin the presentation in Swedish and then continue in English. You are, of course, later on welcome to ask questions in either of these languages. Jag heter Hans Ellegren, jag är ständig sekreterare här på Kungliga Vetenskapsakademin. Till höger om mig här sitter professor Eva Olsson, som är ledamot av Nobelkommittén i fysik. Och till vänster, professor Tors Hans Hansson, också ledamot av Nobelkommittén i fysik och sakkunnig inom ämnet. My name is Hans Ellegren. I'm the Secretary General of the Royal Swedish Academy of Sciences. And to my right is Professor Eva Olsson, member of the Nobel Committee in Physics. And to my left, Professor Tors Hans Hansson, also member of the Nobel Committee in Physics and expert in this field. Årets pris handlar om kvantmekanikens kraft. This year's prize is about the power of quantum mechanics. Kungliga Vetenskapsakademin har idag på morgonen beslutat att utdela 2022 års Nobelpris i fysik i lika delar till Alla, Université Paris-Saclay och École Polytechnique Palaiseau, Frankrike. Till John F. Clauser, J.F. Clauser and Associates, Walnut Creek, Kalifornien, USA. Och till Anton Zeilinger, Universitet Wien, Österrike. Det tilldelas priset för experiment med sammanflätande fotoner som påvisat brott mot Bell-olikheter och banat väg för kvantinformationsvetenskap. The Royal Swedish Academy of Sciences has this morning decided to award the 2022 Nobel Prize in Physics in equal share to Alain Aspect, Université Paris-Saclay, and École Polytechnique Palaiseau, France. John F. Clauser, J.F. Clauser and Associates, Walnut Creek, California, USA. And to Anton Zeilinger, University of Vienna, Austria. They received the prize for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Professor Olsson will now give us a short summary. Please.
Thank you. So, quantum information science is a vibrant and rapidly developing field. It has broad and potential implications in areas such as secure information transfer, quantum computing, and sensing technology. Its origin can be traced to that of quantum mechanics. Its predictions have opened doors to another world, and it has also shaken the very foundations of how we interpret measurements. What today is considered logical, measurable, and quantifiable was initially debated by Niels Bohr and Albert Einstein in philosophical terms. John Bell transformed the philosophical debate into science and provided testable predictions that launched experimental work. This year's Nobel Prize in Physics honors the groundbreaking work and science of the central figures Alain Aspect, John Clauser, and Anton Zeilinger, who took up the challenges of Bell and tackled them in the laboratories. Professor Tors Hans Hansson will present the details of the work. Thank you.
Thank you, Professor Olsson. And I'll leave the word to Professor for a more detailed presentation.
Thank you, Eva, for the introduction. Einstein, in a letter to a colleague, famously wrote, "I'm convinced that he," and he meant God, "does not play dice." And what did he mean with this? Quantum mechanics, the theory of atoms and light, had been immensely successful, but it was also very weird. For instance, take the simplest atom, hydrogen, just one electron moving around the proton. Quantum mechanics couldn't even tell you where the electron was, just the probability to find it somewhere. Einstein didn't like that. He thought that a good theory should give you precise predictions, just as Newton's theory tells you exactly where the moon is in its orbit around the Earth at every moment. Not everybody agreed. Here are two of the founding fathers of quantum mechanics, Niels Bohr and Edwin Schrödinger. They thought that quantum mechanics was okay as it was, didn't need anything more, you just have to accept the peculiarities. And this position was put very clearly in this paper written in 1935 by Edwin Schrödinger. It was an answer to a paper written earlier that year by Einstein, Boris Podolsky, and Nathan Rosen. And they had come up with the thought experiments, which they thought proved, demonstrated that quantum mechanics couldn't be the full story. And now I will explain to you a modern version of that experiment. So here you see a source. This source emits pairs of particles, entangled pairs, Bell pairs. We'll come back to that concept. And they reach Alice and Bob, who makes measurement. They measure a property of these particles that is called spin. And in quantum mechanics, this spin can only take two values, plus or minus. So what happens when you do it many times? Alice will see a sequence of pluses and minuses, plus, minus, plus, plus, minus, minus, plus, etc. Looks completely random. And the same is true for Bob. But the strange thing is that when they compare the measurements, every time Alice sees a plus, Bob will see a minus, and vice versa. And that's very strange, because they are far away from each other, and these particles look exactly the same. Well, perhaps. Let's look at it. Here we have the quantum cards. They look all the same, huh? We shuffle them or entangle them, and then here they go. And they can answer questions on signs. What sign do you have? Plus? What sign do you have? Minus. Okay. Let's take another set of quantum cards. Here they go. What sign? Plus. What sign? Minus. Strange. They look the same. How could they know what sign they have? Well, you see, here it is a trick. That is the following thing. Look, that was a minus, and that was a plus. So each entangled pair had one plus and one minus. I know where the minus went there or there, but it was always one plus and one minus. So, could it be that quantum mechanics was the same? Could it be that there were hidden informations like on the cards? Could it be that nature was a trickster? Okay, just like I was before. Perhaps quantum mechanics is not complete. Perhaps there is something hidden. Einstein would have liked that. And it's a very natural way to think that it would be like that. But years went on, decades went on. No one found such a theory that could explain the experiments with such hidden variables. So this became something more of a philosophical question. Most physicists didn't care very much until in 19 1864, John Bell made an amazing theoretical discovery. By looking at a variation of this experiment that I just told you about, he could show that in that case, the predictions of quantum mechanics couldn't be reproduced by any kind of theory based on hidden variables, however complicated. And when you think of it, that's really strange, because that means that when you measure on one of these particles, it's not so that you just reveal a property that is already there and measure. No, the quantum information about the state is in the full, entangled state of both particles. Indeed, very strange. And so thought the young John Clauser, who said, let's do Bell's experiment. Let's perform it in the lab. Perhaps quantum mechanics isn't right in that situation. Now, that was easy to say, not so easy to do, because with the existing lab equipment, you couldn't perform that experiment. But with collaborators, he came up with a variation of the experiment that could be performed, and he and the late Stuart Friedman went to the lab. They did it, and they found that quantum mechanics works also in this case. Now, there were loopholes. And one particular loophole that John Bell had been very concerned about was that of locality. That means that Alice shouldn't be able to send signals to Bob so they could sort of agree on the result of the measurements. And that was hard to exclude experimentally. But in 1976, Alain Aspect wrote a paper where he proposed such an experiment. And a couple of years later, went to the lab, performed the experiments, and guess, again, quantum mechanics rules. So why is this a big deal? Didn't we know that quantum mechanics works? Well, to explain to you why it's such a big deal, let's go back again to 1935. Here is another paper by Schrödinger, which he says, I would not call entanglement one, but rather the trait of quantum mechanics. So now, much later, in retrospect, we understand that in addition to the profound philosophical and foundational implications of the studies of Bell states, the experiments performed by Clauser and Aspect opened the eyes of the physics community to the depth of Schrödinger's statement and provided tools for creating and manipulating and measuring states of particles that were entangled, although they were far away. And physicists now started to understand that entanglement and Bell pairs is a quantum resource that you can use to achieve amazing new things. And it's no time here to even start to tell you that story. I will just give you one example, which is picked because it illustrates one of the many groundbreaking contributions by the third of this year's laureates, Anton Zeilinger. So to understand this, you have to know that a goal of quantum mechanics today is to build a quantum network. What is that? A quantum network is a series of nodes, and these nodes should be able to communicate via quantum entanglement. In these nodes, you can have quantum devices like encryption devices. How do you build such a network? It's difficult because entanglement is brittle. If you send it to an optical fiber, it very easily gets destroyed. So you need some new trick. And just an amplifier won't work because amplifiers destroy entanglement. So here is the trick, the method that Anton Zeilinger came up with. It's called entanglement swapping. You have two of these Bell pairs, like this, One of the particles here, one, and the other 4, goes far away from each other. The 2 other comes together. Here, you make a measurement, so you entangle particle 2 and 3. And then magically, 1 and 4 becomes entangled, although they had never been close to each other. It's wonderful. So now you can think of doing it in a chain. You do 1, you could do another, you do a third, etc., and you can build up a network. Another method to get long-range entanglement is not to use optical fibers, but to send just light through the air. And I'll just give you one spectacular example of this. And that was in 2018. There was an intercontinental quantum link set up using the Chinese MICUS quantum satellite between the group of Jianwei Pan, the Academy of Science in China, and with Anton Seilinger's group in Austria, over 7,600 kilometers. Pretty amazing. And now we are at the forefront of current research, and I will just end with a few comments. So today we honor 3 physicists whose pioneering experiments showed us that the strange world of entanglement and Bell pairs is not just the micro world of atoms, and certainly not the virtual world of science fiction or mysticism, but it's the real world that we all live in. And researchers now, all over the world, they use entanglement and Bell pairs, both in curiosity-driven fundamental research and in utility-driven applications such as quantum cryptography or quantum computing. Thank you for listening.
Thank you, Professor Hansson. Now we shall see if we may have one of the laureates with us. Professor Anton Seilinger, are you there?
Yes, I'm here.
Professor Anton Seilinger, are you there? Good morning, Professor Seilinger. Please accept our warmest congratulations to receiving the Nobel Prize in Physics.
Thank you very much. It was very kind to receive your phone call just about an hour ago. And I'm still kind of shocked, but it's a very positive shock. Thank you very much.
So were you surprised to get the call?
Yes, I was actually very surprised to get the call. Thank you.
Yeah. I'm sitting here in the session hall of the Royal Swedish Academy of Sciences, and we are at the press conference live here. There are many interested journalists from the international press as well as from Sweden. Would you be ready to take some questions from them?
With pleasure, yes. But I don't understand Swedish, but anyway.
I'm sure they will ask in English at least. Questions?
Right.
SVT?
Hallo, Professor Zeilinger. Glückwünsche, herzliche Glückwünsche. Congratulations. This is Swedish television. I'm curious, could you say something? We can read in the paper here that you demonstrated quantum teleportation, which does sound like something absolutely impossible. Could you say something how it is possible?
Yes. Actually, quantum teleportation uses the features of entanglement. It is not like in the Star Trek films or whatever, transporting something, certainly not a person, over some distance, but the point is using entanglement. You can transfer all the information which is carried by an object over to some other place where the object is so to speak, reconstituted. And this is done, and that is actually the surprising feature. You can transfer the information without knowing the information, because to know the information would violate Heisenberg's uncertainty principle. So far, this has only done with very small particles, and it is certainly absolutely impossible to think of very large objects. But it's fundamentally important for transferring information maybe between quantum computers.
Okay, we have several hands raised here. Was there one here, please?
Yeah, hi, Anton, this is Nordic Chinese Times. First, congratulations on getting this year's Nobel Prize in Physics. Can you kindly share with us what inspired you of
All right. Quantum physics. Anders, that is your area of expertise. It was a little bit hard to understand, I think.
You're referring to Zeilinger's answer,
Yes.
because that I
Yes.
couldn't even hear what he was saying, really, so I
All
found
right.
that really hard. So,
Yes.
But I could say something about teleportation.
Yes.
If it's one. So this is maybe a bit on the side, but it is first one should say that in quantum mechanics, it's impossible to make an exact copy of a system. So you cannot clone a quantum system. There is a so-called no cloning theorem. But what you can do, you can still, if you have a quantum mechanical description of some system, you can send that information, teleport it to another place, and that is quantum teleportation. But there is a price to pay. You always destroy the first copy that you start out from. But there is a way of transferring full quantum information. And this is important can be important in these quantum information applications and so on. But I have no idea what Zeilinger answered. I simply couldn't make it out.
Yes.
But he certainly said much more than that.
Yes. So this prize was given to 3 people on 2 different continents, from US, Austria, and France. Is it common that you work together this broadly in this area?
I mean, they have worked separately, and it also spans over a long time. I mean, the first work was by Friedman and Klaus. So there were 2 persons doing that, but Friedman is no longer with us. And that work was done, when was it, 69, I believe. And then this has been an ongoing effort. And of course, the applications that are being mentioned, and that is really, as Hansson stressed, this is ongoing research. One should also, I would like to bring up also, repeat what Hans said about a theoretical precursor, namely the work by John Bell, who he showed a picture of also. And that was, his work was from 1964. And he really proved, I mean, what is strange, the basis of this whole prize is entanglement. And that means, if, for example, and that is really fundamental to quantum physics. And a simple example is if you have 2 particles well separated, then in general it is so that you cannot describe the properties of one of the particles by itself. So the full description will involve both particles. And in particular, even if these are very widely separated and you make a measurement on one of them, that may instantaneously affect the outcome of a measurement on the other one. There is no transfer of information. This shows that these 2 particles are entangled. You have to view them as a whole. That's the whole basis of this prize. And then, of course, the whole debate that Hans referred to, the work by Einstein, God doesn't play dice and so on. Einstein really didn't like this. He wanted the word to be more classical, so that and then you have this long ongoing discussion whether could there be a more fundamental theory than quantum mechanics, so that there is a more microscopic or more fundamental theory with other variables that behave just like classical things, and those values of those variables would determine the outcome of all experiments. And what John Bell proved was that if you have such a classical theory, Then he proved, with a couple of assumptions, that there is an inequality that will be fulfilled by making certain experiments. And then he showed that quantum mechanics, which one knew was a very well-functioning theory, violated that inequality, which meant that there is no way of replacing quantum mechanics with a so-called hidden variable theory. So it was really, as Hans stressed, a theoretical discovery within quantum mechanics. And since quantum mechanics was so well established, and entanglement was established, lots of things, so it worked so well, it was clear that there could not be any hidden variable theory. And then the whole process with the experiment started and eventually led to, and for a long time that I think was viewed as a bit very basic science, esoteric and so on. But what has happened more recently is, as Hans also stressed, that this is really a resource. One has started to think about more practical applications with cryptography, for example, quantum cryptography, and of course quantum computing, which is so hot today, maybe a bit oversold, but certainly very exciting and very, very interesting. Sorry, long answer.
Very good answer. Thank you for clarifying this for us. It seems like the research has been going on for a very, very, very long time, and the new research build on older research and to make steps forward.
Exactly, and which is the way it usually works. And this also illustrates the time span often from discoveries that are fundamental to when they may come of any practical use, which is of course a problem in this ever ongoing demand from society and not least from politicians that what's the use of this and so on. Really new things, it's really hard to know what the use will be of them 20, 30 years ahead.
Yes. I wonder, do we have any questions from the audience? Just raise your hand and a microphone will come to you.
So how can we use this discovery for the human race?
Yes, so I will repeat the things, bring up the things again that Hans mentioned and I mentioned. Entanglement is really a resource, and the most practical application today, I think, is in quantum cryptography. But then also in the future in quantum computation, where it's very important in many algorithms. But quantum computation, to realize that really in a useful way because of the technological challenges, is still way ahead, I believe, but there are lots of efforts. But in cryptography, there is only one known way of really making a safe cryptographic protocol. If you have Alice and Bob, it's if you have a cryptographic key, how you translate, and that you use that key, that pad, only once, and it's really there's no structure in it, then of course that's perfectly safe. But the problem you have, how do you distribute such a key between two separate persons? But quantum mechanics using entanglement offers a way to safely distribute a key, in the sense that one can check using Bell inequalities whether there has been someone listening in on the distribution of the key. So that's a practical example. I mean, it's not in big use, but it functions and it has been proven in practical applications and so on.
Yes. Another question here, please.
Is there any specific reason these three physicists got it this year, or how come they didn't get it earlier?
That's a good question, and I think one can find part of the answer in how the in the formulation of the prize, that it was awarded to entanglement of photons, which is the technique that has become so important for these applications, and stressing basic importance of entanglement, and then the experimental verification of the violation of Bell inequalities. One should stress that this is a prize in experimental physics, and then also that it has opened up possible new fields of applications. And of course, given that, already going back to what Hans said, referred to these different views on quantum mechanics between Bohr and Einstein. Is it really the full thing, or is there something more basic, as Einstein was looking for? That has sort of lived on, and also the view on how important Bell's work was, that Bell, I would say that Bell really discovered, it was a theoretical discovery which showed that there cannot be any hidden variables. And then some people say, well, that settles it, whereas others would say that experiments is always what settles it, and so on. And so views differ among physicists who perfectly well understand everything. Views still differ on the importance in that respect. But I think the importance of the new thing is really that it has opened up lots of new possible applications.
Mm-hmm. Thank you. And we have one more question here.
Is it okay to ask in Swedish?
Yes.
Please.
Okay. Hur ser den här forskningen ut i framtiden, och hur kan den liksom utvecklas?
So the question is, what will this research look like in the future, and how will it develop? Well, that's the impossible question to answer. But what one should say, that it's an extremely active field. I mean, that it wasn't if you go back 20, 30, 40 years. But given the huge interest in quantum computation in particular, which almost everyone has heard something about, not least, and the companies that are awash in money, like Google and others, putting in so much money, and Microsoft also putting in so much money in this, means that there's huge interest. And there are quantum computation centers coming up all over the place. Sweden is building 100-qubit quantum computer in Gothenburg. Just Denmark announced the other day that they are going to build a practical, useful quantum computer in 12 years. That remains to be seen. So there is a lot of technological development where one tries to build these machines that can, for example, quantum qubits, which are the bits of a quantum computer. And there are many different techniques how one can do that. And it's always very tricky to control and manipulate these things. So that's where the big effort is, in the near future at least. Then, of course, one wants breakthroughs to change really things.
Thank you. Yes, who was first? I think you were first.
The entanglement swap, is this going to function as a classical amplifier, or is this going to have another practical use?
I think the practical use that I know of is that in transmission lines, because you cannot just because of the no cloning theorem, it's hard to, you can't do it by just transferring the information when it's attenuated. But using this swapping technique, you can send signals over lossy transmission lines, fibers. So that's the application I know of. But I know also that it's hampered by a lack of efficient memories of quantum states at present. So because you also have to remember the states and so on.
Thank you. And do you have a question as well, please?
Har det varit en resurskrävande forskning?
Well, has it been a research that has taken a lot of resources? No, I would say, not at the very high end of resources. Now a lot of resources are put into it to try to achieve applications, as I just mentioned. But compared to many others, if you like large-scale, high-energy physics, astrophysics, and so on, it has not. And of course, John Bell used paper and pen, and he did this in his spare time. He was mostly worked on high-energy physics problems, so that took no resources.
Such a big thing and not so much resources. Do we have any questions from our online watchers?
Yes, we have received a few online questions. The first one reads, does this mean that information travels faster than light?
No.
That was very, very clear and fast answer.
Yes, for a change.
Okay.
No information is transmitted in this.
Okay.
Thank you.
Do you have any other questions from online?
No more online questions.
No more?
So the view is really that if you have these two particles, you have to view them as one system, really. You cannot describe them as two separate systems. So that the measurement on one part affects the other part doesn't mean measurement on the other part doesn't mean that the information is transferred from one to the other. It's just changing the state, the description of the whole system. So there's no way of using this to send a signal that one can carry some information.
Yes.
That was actually one of the important loopholes to close also, the so-called locality loopholes. So it doesn't send signals. That it couldn't be that there were some secret signals being transmitted here.
Thank you. Do we have any other questions from the audience? No. It was kind of a tricky topic, especially compared to yesterday, I would say,
Yes.
when it was about evolution or human evolution. But Anders, I wonder, now you have been working with this for a long, long time, and you have had a busy time for a period. What will you do now? Will you just go home, lay on your sofa, read a novel?
Probably.
Probably. And when does the work start again?
As everyone who is involved in this, and much more than I am, people do their research, their teaching. There's a set number of professors at universities that do that. So that's what we do. And then, of course, it's all the running and meetings and things that everyone is doing. But so that's our standard life.
Your standard life. Sounds
and then, of course, the new round starts for next year's prize.
And when does that start?
Well, it builds on what one has, but I don't know exactly. But it starts early on, actually. So because one issues these evaluations, and that is already ongoing.
Okay, that's great. I would like to thank you very much, Anders, for coming here today and clarifying for us the Nobel Prize in Physics this year. And thank you, all you students who came to the Nobel Prize Museum. You're, of course, welcome back. And thank you, all of you who have been watching this streaming on YouTube. And, of course, you're also welcome to the museum. Thank you.
Thank you for the attention. Thank you.